Hi everybody, welcome back. In this section we're going to come back to a problem we looked at very early on in the course, and that was trying to figure out how many trees there are on n vertices. So we looked at a few small examples, but in this case we're now going to come back to it and we're going to come at it from a new angle, and we're going to see that we can count the number of trees there are on n vertices by using a result of Cayley. And this is known as Cayley's formula. So the way we're going to think about this, though, is we're going to think about this as how many spanning trees are there in case of n. And that's equivalent to saying how many trees are there on n vertices labeled 1 to n. And so let's look at a few small examples first. This is the kind of thing we would have done at the beginning of the course. Now, how many trees are there on one vertex? Well, there's just one of them, and it's the vertex itself. So if we let this script t sub n denote the set of all trees, then in that first box, that's the set t1. And here, little t is just going to be how many there are. So little t1 is just one. There's only one tree on one vertex. Or in other words, for the complete graph on one vertice, there's only one spanning tree. How about for the complete graph on two vertices? Well, there's also only one spanning tree, and there it is. And so we also get that little t of 2 is 1. So now here's where things start to get a little bit more interesting. How many spanning trees are there on the complete graph of 3 vertices? Well, we can think about how we would count those. We've got 3 vertices to work with. So 1n could start with a 1, and then the other 2 vertices could appear 2, 3, or 3, 2. And that takes care of all of the trees that has 1 as a leaf. So then the other option is, what if 1 is the middle vertex? Well, then there's just this third tree there. So what we have found is that we've listed them all. This is T3. And the number of them is 3. So how about with 4 vertices? How many spanning trees are there on the complete graph of 4 vertices? Well, we've listed them all here. And I've done them systematically. I said, what happens if 1 is a leaf? Well, if 1 is a leaf, then next to it could be 2. And then 3 and 4 could either appear in order or out of order. And that exhausts all the possibilities where we have 1 as a leaf next to 2. What if 1 is still a leaf, but it's adjacent to 3? Well, then 2 and 4 could appear in order or out of order, and so on. And we just systematically go through all of these options. That gets us all the paths. And then the last 4 down in the bottom are really about vertices of degree 3. 1 could be a vertex of degree 3, or 2 could, or 3 could, or 4 could. And so there's our listing of all the options. So this takes care of listing all of T4, and we see that T4 is therefore, and we'll count them off, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of them. So there's 16 spanning trees of the complete graph on 4 vertices. And so we've just listed those values here. T1 is 1, T2 is 1, T3 is 3, and T4 is 16. Now this approach of exhaustively listing and counting, we're pretty much at our limit here. If we were going to go and try to do this with 5 vertices, it's going to take us quite a long time. So can we revisit counting the number of spanning trees on 4 vertices in another way? And so that's our question. Could we have found T4 without listing them all? And the idea is yes, we could. And I'll go through a couple of methods of how we could do this. So method 1 for finding little t4. So the idea is we've got 4 vertices, and I'll just draw them like this. And one thing I want you to notice is that I am going to use the space off to the right, so I'm going to try not to go into that area because I'm going to use that next when we look at the next case. So I'm just going to fit all my work onto the left-hand side. And so what do we want to do? Well, we want to build a spanning tree on this. So a tree uses how many? So there's 4 vertices, so there'd be 3 edges. So 3 of the 6 edges in K4. We have to avoid a triangle. So in other words, a 3 cycle. That's the only thing we're trying to avoid. So can I count those? Absolutely, I can count those. So I've got to use 3 of the 6 edges. So of the 6 edges, I'm going to choose 3 of them. So this is the ways to choose 3 from 6 edges. The problem is I may not get a tree if I just arbitrarily select 3 of the 6 edges. What happens if I selected 3 edges that formed a triangle? Well, then I don't have a tree. So I perhaps am counting too much here. What I need to do is I need to take away all the triangles I created. So how would I create a triangle? Well, a triangle is created by just of the 4 vertices selecting 3 of them. So these are the 3 cycles to avoid. And we got these by a 3 cycle is made up of choosing 3 of the 4 vertices. So those are what I'm going to avoid. So for example, if I want to avoid a triangle that contains vertices 1, 3, and 4, this is the triangle I'm trying to avoid, and that one is just characterized by the way I described it, by choosing these 3 of the 4 vertices. So that's why over here I'm counting edges, but then to avoid triangles, I'm noticing that I can count the triangles by just counting the collections of 3 of the 4 vertices. And so there we go. That's how many trees there are going to be on these 4 vertices within K sub 4. So what is it? Well, it's 6 choose 3. So that's 6 times 5 times 4 divided by 3 factorial, which is 6, minus 4 choose 3, which is 4. And so that's 5 times 4 minus 4, or 16. And so there are 16 spanning trees of K4. And we can see that matches what we found before by actually listing them. Could we count this in another way? Let's try a different way of counting. So we'll call this method 2. And here we're going to just look at what are the kinds of trees there are on 4 vertices. What are their shapes? Up to isomorphism, what do they look like? So up to isomorphism, trees on 4 vertices look like, well, it could look like this. There could be a vertex of degree 3 and then 3 leaves hanging off it, or it could be a path. And that's it. Those are all the kinds of trees we can have up to isomorphism on 4 vertices. Now we just need to look at how to apply the labels. So we will figure out how many ways can we apply labels. So the labels 1, 2, 3, and 4 to the vertices. So let's look at this first one. Well, I could pick this middle vertex and I could apply any of the 4 labels to it. And then once I apply the 4 labels, the other 3 just get distributed amongst the leaves. Of the 4 vertices, just choose one of them to be the one of degree 3, and then the other 3 just become the leaves. What about in the other case? Well, in this case of a path, I could just apply the labels in any way possible, for which there are 4 factorial ways. But then I have to realize that reading the path forward and backwards is exactly the same path, so I'd have to divide by 2. So we have 4 factorial divided by 2. And that's the number of ways we could apply labels to the first and the second trees. And so this is our total number of spanning trees. And that's going to be 4 plus 4 factorial divided by 2. That's 12, or 16. And there we go. We got the same answer of 16 in a different way. Now, the question is, can we figure out what Tn is in general? Well, before we go to Tn in general, let's figure out if we can do T5. So can we find T5? it turns out we can, and we can do it much in the same way we did this one down here. We know what the form of a tree on 5 vertices must be. So up to isomorphism. A tree on 5 vertices has the form. So what is it going to look like? Well, there could be a vertex of degree 4, in which case it would look like this. Or there could be a vertex of degree 3. And with that vertex of degree 3, there'd be 2 leaves hanging off it, and then for one of the other vertices hanging off it, there's another edge and a vertex hanging off that. Or we could have a path. So 1, 2, 3, 4, 5. And so those are all the possible trees up to isomorphism we have on 5 vertices. Now we just count how many ways there are to apply labels. And we do it the same way we did before. In this first case, there are 5 ways to pick the label for that inner vertex, and then the remaining vertex gets distributed among the leaves. So there's 5 ways to pick middle label. So pick middle label. So that's for that first graph. How about the next one? Well, there's 5 ways to pick the label for the vertex of degree 3. So there's 5 choices for that. Once that is picked, then what? Well, then I'm going to have to distribute the other 4 labels amongst these vertices. So there's a vertex of degree 2. So there's 4 ways to choose that one. So I picked now the label for that one and the label for that one. Now I just need to distribute the rest. Well, these two are essentially interchangeable. However I label them, I could always switch the labels and it would be the same graph. So of those remaining 3 vertices, there are 3 choose 2 ways to fill the labels in for these ones, and then whatever's left over gets filled there. So at this point, there are 3 choose 2 ways to fill these labels. And for a path of length 5, there are 5 factorial ways to apply the labels, but forwards or backwards is the same path, and so we have to divide by 2. And there we go. We get our total number of ways we can apply the labels. This is 5 plus 5 times 4 times 3. So that's 20 times 3, or 60. Plus 5 factorial divided by 2. 5 factorial is 120 divided by 2. That's also 60. And so we get an answer of 125. So we know how many spanning trees there are in K5. There's 125 of them. Now there's a problem with continuing this approach, because if we try to do this for T6, for example, I'd need to know all of the trees on 6 vertices up to isomorphism and then count how many ways there are to apply the labels. But that becomes a challenging problem as well, figuring out how many trees there are up to isomorphism for a specific number of vertices. So in the small cases, we are able to just list those, but as soon as n becomes larger, this becomes a bit infeasible as well. So what we are interested in is, what is Tn in general, and how can we count it? So let's go back up and see if we can spot a pattern so far. So we've just worked out T5, that's 125. And do we spot a pattern with these numbers? Well, 125, that is 5 cubed. So that might be worth noting, 5 cubed. And it's worth noting because T sub 5 is 5 to some power. T sub 4 is 4 to some power. Okay, so let's list these ones out. That's 4 squared. Oh, and T sub 3 also follows that same pattern. It is 3 to a power. In this case, the power is 1. So it's looking like it's 5 to a power, 4 to a power, 3 to a power. If I look at what those powers are, they are dropping. Does this pattern continue to hold? Well, that should be a 2 to the 0 if it does, and it is. 2 to the 0 is 1. Let's see, does it continue to hold all the way down? Well, this should be a 1 to the, well, minus 1. 1 to the minus 1, that's still 1. Oh, and that holds as well. So this looks like a pattern that we've just discovered by just working out the first few. Now, in general practice, when you find a pattern, it's tempting to think, okay, great, I've proven it. But we haven't proven anything. All we've done is worked out a few cases and we've observed a pattern. So the question is, does this pattern hold? And if it does, how do we prove it? And that's where Cayley's formula comes in. Cayley's formula says, yes, this pattern does hold. The number of spanning trees of Kn is n to the n minus 2. And it's stated here for n greater than or equal to 2, but we've also seen that it works for n equal to 1 as well. So how can we prove this? Well, Heinz Prüfer in 1918 proved this by using this idea of what is called now a Prüfer code. And the way he did this was, he did it as follows. He says, let's consider the set of all trees, spanning trees, on Kn. And then let's consider the set, in this case, it's just the set of sequences in the vertex labels of length n minus 2. So you can think of this as just the set of all words of length n minus 2 in the vertex labels. So that's Pn. And the key idea here is that Pn, these are just the words. So I'll write down a general one. There's a first letter, a second letter, all the way down to n minus 2. And these letters are coming from the n labels on the vertices. So we've got n choices for each. So that's something we can easily count. This is something we counted back at the beginning of the course. The size of the set would just be n times all the way down to n, or n to the n minus 2. So we know the size of this set. And what Heinz Prüfer did was, he said, for every tree, we can find a corresponding word that uniquely defines that tree. And that's known as this Prüfer code, which is given by this function PRU. So there's this function PRU that takes in as a tree and returns a word or a sequence of length n minus 2 in the vertex labels. And it turns out it is a bijection. It's 1 to 1, it's onto, so it has an inverse. And I'm just going to give you an example, or a couple of examples, in the case, let's say, where n is 4. So we could have 1, here's our tree. So this is how we can visualize it. We've got our tree over here, 1, 2, 3, 4. We've got another tree, maybe this one had a middle vertex of 3, and a 1, and a 2, and a 4. Or we could have another tree that looks like this, and it was, let's say 2, 1, 3, 4. We've got all of the trees in this set. I've only drawn 3 of them, but we could have all 16 of the trees drawn here. And what the Prüfer code does is it takes a tree in and it returns a word. In this case, the word it returns is 1, 1. I'll use commas to separate them. So it's 1, 1. This tree would get mapped to the word 3, 3, or the sequence 3, 3, or the code, as we're going to call it, 3, 3. This one is going to get mapped to 1, 2. I haven't told you how I'm getting these codes yet. That's what we're going to do on the next slide. But here is the big picture idea. So Heinz Prüfer said for each tree, you can assign a code. And a code is going to be a word in Pn. And it's going to turn out that this is a bijection. So the size of Tn is precisely the size of Pn, and the size of Pn is something we can count. So what we get is, we get that the size of Tn is equal to the size of Pn, which is n to the n minus 2, and therefore the total number of spanning trees of Kn is n to the n minus 2, which is Cayley's formula. And so what we'll do now is we will go ahead and introduce the technique for finding the code, and then we will also do the opposite. Given a code, we will go ahead and give a way to find the corresponding tree. So we're going to show that there is this bijection. So how do we get the Prüfer code? So here we describe the algorithm. It takes as input a tree on n vertices, and it returns a code of length n minus 2. And the way it does it is as follows. We run a loop from 1 to n minus 2. And we look for the leaf with the smallest vertex label. Once we find that, then we look at its unique neighbor and write down the value of that unique neighbor. And then we remove that leaf and that edge that connect it to the unique neighbor, and then go and do it again. So here's what it looks like in practice. We're going to find the Prüfer code for it. So we look at what is the smallest valued leaf. And there it is, it's 2. Its unique neighbor is 7. So I write down 7. I get rid of 2 and the edge connecting it. And then I just repeat the process. And this is going to generate the code. So repeating the process, what's the smallest labeled leaf? That's the 3. Its neighbor is 6, and now get rid of it. And then do it again. What is the smallest leaf? That's the 4. Write down its neighbor. That's the 7. Get rid of it. Smallest leaf is 5. Its neighbor is 6. Get rid of it. Smallest leaf is 8. Its neighbor is 7. So now I get rid of that leaf. Now what's the smallest leaf? The smallest leaf is this one, because all we've got is a path of length 4 now. This is all we're staring at. The smallest leaf is the 7. Its neighbor is 6. We can now get rid of it. Now I'm down to a path of length 2. The smallest leaf is the 6. Its neighbor is 1, and I get rid of it. And now we have performed our loop n minus 2 times. In this case, n is 9, so we've performed it 7 times. And then what it says is, you're done. You've got your Prüfer code. And so there is our Prüfer code. That is our word of length 7. And one thing to observe at this point is our algorithm terminated with a single edge and 2 vertices. And you might want to think about what happens if I ran the algorithm on a single edge with 2 vertices. Well, we would just get the empty word back because there's only one tree. There's only one spanning tree of K2. And the corresponding Prüfer code is the empty word. Okay, so we've got our method for going from tree to code. A couple of things to observe. How many times did a vertex appear in the sequence? So let's just look at some of these. 1, it appeared once in the sequence. 6 appeared 1, 2, 3 times. 7 appeared 3 times. Notice that each time we wrote down a vertex label, it was because there was a leaf attached to it, and we got rid of that leaf. And so our observation is that the number of times a vertex appears in the code is precisely its degree minus 1. The other thing to notice is, let's imagine looking at the code itself and seeing, can I get back to the tree? Well, what's the first step to observe? The first step to observe is that whatever vertex I removed at the very start to start making this code, so that gave me the 7, whatever vertex it is that I removed, it's never going to appear in this code because I've removed it. So the smallest number that doesn't appear in this code is precisely that number that I would have thrown away at the beginning. And so 2 is the smallest number that doesn't appear in that code. So that means that 2 should have been connected to 7 in the original graph. And that's exactly what happened in our first step. So the second observation is the smallest label that's not in our code is the one that's adjacent to the first member of our code. So 2 is the smallest number not in there. It would be adjacent to 7. That observation is what gives rise to the tree algorithm, which gives us the code as input and returns the tree as output. And so here's how that algorithm works. So we start with our vertex set, and we've got our code of length n minus 2. So code's length n minus 2 means we are producing a tree on n vertices. We're going to set L to be the entire vertex set, and our edge set is empty. So this is going to consist of the edges that we're using to build our tree. And then we run our loop from 1 to n minus 2. Consider the first element in our list of vertices that's not in the current code I'm looking at. And then we just add that edge that connects that vertex to the first character in the code we're looking at. And then we remove the vertex y from L, and then just repeat the process. So the best way to get a hold of what this algorithm is saying is to just do it as an example. So here's our code. It's length 5. So that means we are looking for a tree on 7 vertices. So the length plus 2 is the size of the tree we're looking for. And so let's write down that code. 3, 4, 5, 3, 1. And I'm going to do all my bookkeeping right on top of this code itself. So the first thing to observe is the smallest number that doesn't appear in this code is the number 2. And so the 2 had to be adjacent to the 3. So we've got that 3 and 2 are connected by an edge. And now we've dealt with that vertex 3, so we can continue on. So this code here is going to be the proofer code for the tree that's going to fill in the spot. And then there was that last little bit that said the 2 is now connected to the 3. So what we're doing is we're basically doing a recursion argument here. We've now got this code and I need to build the tree for that. But I can't forget the fact that I've already used vertex label 2, so that's why I'm bookkeeping it here. So then what's next? Well, now I look for what is the smallest label that's not in this proofer code and hasn't already been used. So I like to just look at it as what's the smallest number that's not in this list. So we've got a 1, a 2, a 3, a 4, a 5. We don't have a 6. So that means I can stick the 6 here, and it's going to have to be adjacent to the 4. So I'll put a 4, put a 6 there, and then we've dealt with the 4. Now what's the smallest label that doesn't appear in this list? Well, I got a 1, a 2, a 3. I don't have a 4 now. So we've got a 4. It's got to be connected to the 5. So there's our 4 and 5, and I can get rid of that. And then I just keep going. What's the smallest label that doesn't appear in this list? I have a 1, a 2, a 3, a 4. I don't have a 5 now. So 5's connected to the 3. So I got an edge that goes like that. And now what's the smallest vertex label that doesn't appear in this list? That we've got a 1, a 2. We don't have a 3 anymore. So I've got my 3. 3's connected to 1, so I get a 1 that goes off like that. And we are done. We are at the end, but I still have one more vertex to consider. That's the smallest vertex that isn't in this list. We've got a 1, a 2, a 3, a 4, a 5, a 6. We don't have a 7, so we also have a 7 hanging off of that 1 as well. And there we go. And we can redraw this. We can redraw it as 7 to 1 to 3 to 5 to 4 to 6, and then the 2 is hanging off of the 3. And so there's our redrawn version of the same tree. So there's our tree that corresponds to this proofer code. Let's do a quick check. Always a good idea to do a check. We've now got the tree drawn, so we know we can quickly get the code from it. What's the smallest leaf? The smallest leaf is the 2. Its neighbor is the 3. So we'd write down a 3, and then we'd get rid of that 2. Now what's the smallest leaf? The smallest leaf is a 6. Its neighbor is the 4. So we'd write down a 4, and then the smallest leaf is a 4, so then we'd write down a 5. And then the smallest leaf is a 5. We'd write down the 3. So we get a 4, 5, and 3. And then the point is we're down to this path, and then the smallest leaf is the 3. It's adjacent to the 1, so we get a 1. And we are now left with just the 7 and the 1. And so we're done, and we got our code. It's 3, 4, 5, 3, 1, which is exactly the one we have up here. So just as a quick check, yep, we got it. Well, that's it for this section. All we wanted to do was introduce Cayley's formula for the number of spanning trees there are in the complete graph, and the proofer codes for justifying that formula, and how to take a tree, produce a proofer code, and also how to start with a proofer code and generate the corresponding tree, just so we can see that there is this one-to-one correspondence between spanning trees and words of length n-2. All right, thanks very much for watching, and we'll see you again next time.